A British Prime Minister was once asked what was the most difficult thing about politics, and he answered, "Events, dear boy, events." In software, I think it's probably the other way around. If you look at where the big successful web companies and ultra high performance finance companies nearly always end up, it's with asynchronous event-based architectures. Why is that? We all learn to program in a very different way. So why is that too? Oh, and what is it that one of my friends memorably once called the crack cocaine of computer programming? That's our topic for today. Hi, I'm Dave Farley of Continuous Delivery. Welcome to my channel. If you haven't been here before, please do hit subscribe, and if you enjoy the content today, hit like as well. Today I'd like to talk about synchronous and asynchronous programming. I have what is almost certainly an unfashionable view on this. I've spoken about reactive and actor-based systems before on this channel, but I was listening recently to a conference talk by Randy Shoup, and it reminded me that as well as high performance and ultra resilient systems, nearly all of the big famous web companies end up with reactive asynchronous architectures. But few people start new projects from there. Before we get into exploring why that is the case and what the benefits of thinking differently may be, let me thank our sponsors. Equal Experts, Tricentis, Transfig, Launch Darkly and Roost. All of these companies offer products and services that are well aligned with the topics that we discuss on this channel every week. So if you're looking for excellence in continuous delivery and software engineering, click on the links in the description below to check them out. Randy's talk about describing the journey that the big web companies nearly all took brought to mind a series of lunchtime and sometimes pub conversations that I used to have with my friend and former colleague Martin Thompson when we were working on building the financial exchange at LMAX. The LMAX system was and is ultra high performance. We knew from the outset that performance was a business imperative for us, and we began our design, like lots of others, assuming that at least in parts it would need to be synchronous. We were experienced developers when we started out, and we knew that if you wanted high performance, then asynchronous was definitely the way to go. But we also assumed that life would be a lot simpler if we also used synchronous communications for the slower bits. We later realized that this was a big mistake. A lot of the problems that we hit were as a result of the synchronous parts rather than the asynchronous parts. At some point, Martin and I were grumbling about the current problem of the day, and Martin said, "Synchronous programming is like the crack cocaine of software development." It's a memorable phrase, and while neither of us would want to belittle the horrors of drug addiction, it's also quite a descriptive metaphor for programming, really. All of us take our first steps with programming with synchronous programming languages. Ideas like concurrency need to wait for a bit before we're ready to deal with them, because these are really difficult to think about and understand, aren't they? Well, maybe not, but we'll get to that later on. If we call a function, we expect our code to sit and wait for a reply before it moves on. This seems to make perfect sense. It makes learning to program easier. It's really quite an addictive idea. The trouble is that computers and the real world don't really work like that. If you and I are talking and you ask me a question, your brain doesn't stop processing while I hunt for an answer. You're thinking about other things. Maybe you start off thinking something like, "I wonder how Dave will answer my question." But if I take too long to answer, your mind will wander off and you'll start thinking about, I don't know, the football results or what you'll have for dinner later. Or maybe you'll even start working on something new while you wait for me to respond. If I go to a real bookshop to buy a book, I may have to queue if it's busy. But while I'm in the queue, I am probably chatting with my friends or browsing the books in the racks nearby, or maybe checking my messages on my phone. Again, the world hasn't stopped because I'm queuing to pay for a book. The real world is concurrent and asynchronous. So as we begin to build more and more complex software systems, the more and more that concurrency and asynchrony begin to surface as problems. The reasons that Martin and I were grumbling was because we'd reached the point where it was starting to look much simpler to just embrace the asynchrony and go with the flow for everything. As soon as we made that decision, nearly everything got simpler. I think that both of us came to the conclusion that the reason that asynchronous programming has a reputation for being more difficult had more to do with how people learned to program and how we adopted the leaky abstraction of synchronous programming for most programming languages, rather than any inherent complexity in asynchrony itself, which we nearly always get to anyway. It's not that the complexities don't exist in synchronous programming, they do. These complexities are unavoidable and surface in much more unpleasant ways as long as we're trying to hide behind some form of synchronous facade. Let's look at that assertion in a bit more detail. If we write some single-threaded code that's meant to run on a single computer, things are pretty simple. We can make function calls, our code can wait for the result, and the code is easy to reason about and easy to write. But it's been a long time since computers, even your phone, actually worked like that. My phone has 6 general purpose cores and 5 GPU cores, so 11 in all. So if my program does one thing at a time on a single thread, the very best that I can do if I completely max out my code and the processor it's running on is to run at 9% of the capacity of my phone. In reality, for lots of things, that's probably fine. Modern processors are pretty fast after all. But what this says is that there's a hard cap on how complex my code can be if it's to be responsive and nice to use. That cap is set at about 9% of what it could be on my phone, unless we were to accept concurrency as part of our solution. But the reason why we all learn to program with these simple synchronous calls to begin with is because concurrency is a lot more complex, at least while we're trying to maintain everything in synchronization. My experience of concurrency is that the more that you learn about it, the more nervous it should make you. If not, then you don't really understand the problem yet. But once again, this is really as a result of this strange, unrealistic programming model that we layer on top, and that we've all adopted as normal. If you'd like to learn more about the kind of design thinking that led us to these sorts of conclusions, we were driven by a strong focus on separation of concerns, reducing coupling between our infrastructure and our business logic, and better abstraction of the core of our system. All of which I describe in some detail in my best-selling book, Modern Software Engineering. There's a link in the description to that below too. The reason why concurrency is scary is because it can break the illusion of this nice synchronous programming model. If I make a call to a function and wait for a result, what happens if the system is concurrent? Well, it really depends on the data. If there's this shared writable data anywhere, then the real answer is we don't know what happens. It's a complex problem. The value of our inputs could change as we are in the middle of processing them. The value of our outputs could be invalidated while we're in the middle of returning them. Actually, at the level of how our computers actually work, data can be overwritten or scrambled in other unpredictable ways, even while we're in the middle of even tiny operations on it, unless we actively program to avoid it. If that idea doesn't make you feel nervous about concurrency, then I haven't explained it well enough. So we've come up with all sorts of clever tricks to try and manage the reality of the concurrency in our systems, while giving the illusion of synchrony. We have locks and semaphores to protect our data. And we have what, to me, seem like fairly crazy ideas like asynchronous await, where the idea is to write asynchronous code, but to make it look a bit like synchronous code. All of these things come at a cost. And when we take the next step in complexity and decide that our system needs to be multi-user, we ramp up the complexity even further. Now we have lots of new problems. If we haven't already taken the step into concurrent systems, now we are forced to do so. If not, then our whole system is single-threaded and it will only be available to one user at a time. If we have made the decision to add concurrency, now we need to redesign our code to be multi-threaded so that people don't have to wait for responses while someone else is using the system. This adds a lot of new complexity to the design of our system, and things get even worse if, again, there's any shared writable data anywhere. Because if we don't address this carefully, our system is now non-deterministic. That is, the results are random, at the whim of the timing of our different threads. So we have to start thinking about ideas like locks and semaphores and worry a lot about shared data. One of the reasons I would argue for the enormous success of the relational database programming model is that it presented a relatively simple way of dealing with this problem. That largely hid concurrency from programmers. We could deal with some inputs and wrap all of the data related to them in a transaction, and this would isolate information inside from other threads of execution. The next step up is the big one, the move to distributed concurrent systems. Now the problems get really complicated. As soon as you distribute processing and information, you add a huge amount of new ways for things to go wrong. Here's an example. If I have a couple of programs that talk across a network, how many ways can this conversation go wrong? Well, there may be a bug in application 1 that means it fails before it's able to talk to application 2. App 1 may not be able to establish a connection to the network and so can't send its messages. The network may fail while the information from App 1 is en route and so never arrives at App 2. App 2 may not have been able to connect to the network. App 2 may be too busy to process the call when it arrives. App 2 may not be able to understand the message from App 1. And then there may be a bug in App 2. And then all of these possible failures can happen in reverse when App 2 tries to send a response back to App 1. If we keep using this weirdly unrealistic model for communication and try to maintain the illusion of synchronous behavior between these two apps, these problems are almost impossible to deal with, at least at any kind of scale. Just think about it for a moment. Which of these failures can either App 1 or App 2 know about from their perspective? We have to code with the expectation that any of these things could happen. If App 1 is sitting waiting for a response from App 2 and App 2 has crashed or is struggling to cope with load or unable to communicate the result, App 1 is stuck. And it can't tell the difference between why it's stuck, these different kinds of failure. This is a problem because each of these failures could leave the system as a whole in a completely different state. So now there are several different ways to fail, each requiring a different action to recover and no way of being able to tell the difference between the failures. So how can we tell which fix to apply? We add loads of complexity to distributed systems to try and deal with this problem. It also means that anything that's waiting for App 1 is now also blocked in the same way if it's synchronous. In this kind of distributed system, errors propagate through the whole system. Systems like these are prone to catastrophic failures. The costs of the addiction are starting to show now. So what is the difference between synchronous and asynchronous? The problems described here don't go away in an asynchronous system. But the great thing with a truly asynchronous approach is that from the perspective of the service or application, the answer to these problems is always the same. You wait for a message to arrive, you process it on a single thread, and you send your results as a new asynchronous message. In normal operation, even when we want the equivalent of a fast synchronous response, this asynchronous approach is faster. Think about that for a moment. In a synchronous request-response communications approach, App 1 sends a message, stops its own process and waits for a response. Nothing else can happen in App 1 now until the response arrives, unless we decide to do something complicated like make App 1 internally multi-threaded in the midst of our business logic. App 2 receives the message, processes it and sends a response. App 1 receives the reply, restarts itself and processes the reply. Now let's look at the asynchronous case. App 1 sends the message. It's now available to do other things while it waits for a response. App 2 receives the message, processes it and sends a reply as a new asynchronous message. At some point, doesn't matter when, App 1 receives the reply and processes it. So it's doing mostly the same things, but it's doing fewer things. It's no longer doing the extra work of stopping and restarting itself. So in normal operation, the asynchronous version is faster and more flexible. Now let's look at the failure cases again. All the same points of failure exist. As before, there are lots of kinds of failure that App1 can't detect. And even if it can't know the state of the system and so how to respond. But now, in the asynchronous case, that doesn't matter so much. Because all App1 ever does is wait for a message, do some internal work on it, and send another in response. For this, we need to add a couple of ideas in order delivery of messages and idempotence. Idempotence is the idea that an operation can be applied many times, but you're going to get the same result. You're only going to get the result as though the message happened once. So we'd like at least once delivery and idempotence. Our messages will get there, but only change things once. Here's an asynchronous version of App1 and App2 again. App1 can send messages and not be stalled waiting for a connection or anything else. The messages are stored in a ring buffer until the separate sender process is ready to put them on the wire. Each message has a unique sequence number. This will allow us to order messages on this topic. So if we send a message and it is lost in transmission, App1 is unaware, but there's a copy of the message in the ring buffer. Meanwhile, App2 has been keeping track of incoming messages and assigning each to a slot in its own input ring buffer, which slot is determined by the sequence number on the message. So now, if message 4 arrives when App2 is expecting message 3, the messaging infrastructure can notify App1's messaging infrastructure of the problem, saying something like, I was expecting message 3 and you sent message 4. Notice, the business logic of App1 and App2 are not involved in this conversation. All this is happening under the covers in the infrastructure from their perspective. So now, App1's message infrastructure can reset its cursor and replay message 3 and all subsequent messages. So App2 gets the message it expected and can continue doing work. If we send a message that App2 has already seen, it can simply ignore it and not pass it on to the business logic. So now we have in-order messaging and idempotence. Think what this means from the perspective of App1 and App2. App1 sent a message. In the normal case, it gets there and is processed faster than for a synchronous call. But in the non-normal case of a failure, the message will eventually get to App2, however bad the failure, even if that means rebuilding the data center before restarting the new version of App2 and it responding to the first message it receives with, sorry, I was expecting message 1. Of course, there's more detail than this. It's limited by queue depth or ring buffer size, but there are all sorts of tricks that we can play in the infrastructure outside of App1 and App2, so that now these problems can be solved as technical infrastructure problems and not part of the business logic of our applications. That's a rather nice separation of concerns. The ability to replay the history of interactions in our systems is a very valuable property too. For example, it means that I can replay a recording of the events that led up to a crash in production in a test environment and then debug the moment of the crash. The technical point here is that no information is lost if we record all of the events and our system only communicates via events. Which is not true when we take that synchronous style database snapshot freeze frame of the operation of our system. None of this means that failures can't happen in asynchronous systems, of course. But it does mean that whatever the nature of the failure, they're much easier to recover from. And in most cases, recovery simply means replaying some messages. So it does not need any special coding in the business logic of our systems to handle these kinds of errors. This is where the claim that this is simpler comes from. The example that I showed using the ring buffers is a high-level view of why we wrote the open-sourced disruptor while I was at LMAX. In addition to the idempotence and assured delivery, the disruptor allowed us to implement storage and clustering and many other features without our applications or services knowing anything at all about them, or needing to change their design in any way to support them. There's a link to the Disruptor open source project in the description of the video below. There's a lot more to this programming model than I've sketched here, of course, and there is more on this channel that describes different aspects of it. But I often wonder if software development in general would be better if we all learned to program with the constraint that the only intermodule communications that was allowed was via asynchronous messages. Erlang, anyone? Thanks for watching, and if you enjoy my stuff, please consider supporting our work on this channel by joining our Patreon community. There are lots of great benefits there. Thank you again.